Hi everyone. I'm back. It's good to be back. Honestly, I've missed making YouTube videos. I'm not sure if this is going to be like a regular a return to regular uploads. I don't think it is. That's still a little bit of a ways away. But I am here because I want to introduce my the software I've been building and have a video up that explains how to use it. But to the more regular audience of my videos, if I still even have that, I want to say a little bit about where I've been and where this channel is going. So if you are only here for information about how to use Overseer, you probably want to skip ahead about a minute or so. But if not, first of all, there's a few reasons why I haven't uploaded any videos since I finished my Marxism series. The first reason is that simply I was extremely burnt out after I finished that series. I needed a break. The second reason is that I don't make videos unless I have something to teach in the videos. And I felt like after I made that series, I had kind of peaked, and I needed to spend a few years doing research and actually working on stuff that I would eventually become somebody with the knowledge to present something more than what I did in those videos. And I'm almost at that point. I am at that point a little bit. And then the third reason, of course, is that the circumstances that allowed me the time and space to make those videos, as all circumstances of such a kind are, were temporary. I was a grad student. I had mostly finished my the work that I needed to do, research work on my thesis, and I still had I was kind of coasting on a final year of funding that and so I was just making those videos because I had a lot of time and I wanted to. And then I finished my PhD. And I had to find a job, and it was a really rough time. I think everybody, I don't think I need to get into how difficult the job market is right now for anybody in general. I eventually did find a pretty good job, not as a math professor, but as a computer science professor, not tenure track. And because I am not a computer scientist, that was a pretty rough adjustment period, and that's the real reason why. That's the biggest reason why I've been gone for the last several years, is because it's been an extremely long and difficult adjustment period, getting used to teaching in a completely new field that I had to basically learn while I was teaching it. But I am at that point, and to some extent, what I have to present here is the product of that struggle. When I was applying for the job, I really kind of had this in mind. I wanted to get better at programming in order to make something like this because something like this, as far as I could tell, didn't exist, and I needed it. And now I've built it. It exists, and I'm excited to show you guys it. It's called Overseer. So let's talk about what Overseer is, because it's not unrelated to the Marxism series of videos that I did, actually. So what is Overseer? The jokey kind of tagline I kind of give people is, it's Desmos, but make it Turing complete. Now, that probably doesn't mean a whole lot to most of you, so let's back up and start with the question, well, what is Desmos? Well, Desmos is, I think most of you are probably familiar with it. It's a graphing calculator. It's just a browser-based fancy graphing calculator, but it's pretty uncontestedly, I think, the best one. Right, I mean, here it is, and you can just kind of do exactly what you would want to do. You could say, like, f of x equals sine of x, and then here's my sine of x, and, it looks really nice, and what's really nice about it is that you can do things like this. I can put an a here, and then it suggests that I add a slider for a, and then I can add the slider, and then I can just kind of adjust it, and you can see the adjustments in real time. It's just a really slick interface. That's kind of why Desmos is so nice. I can add another one. I can say g of x equals cosine of x, and you can kind of see them. And then I can maybe put like a b here and have a b slider, and then I can also put the same b here, and then I can like change the frequency, and it's just really fun. Like, Desmos is just a really nice tool for, if you're learning math, to just get a feel for what functions look like, what happens to functions as you do this or that to them. What happens when you compose this or that function. I can take like f of g of x, and you get all sorts of stuff. It's really fun. So yeah, it's just a very useful tool for learning math, and also it's a very useful tool for demonstrating things mathematically. Sometimes you can build really nice, comprehensive educational models in Desmos, which is something that I did a lot of. And most of, if you've watched my videos, you know exactly what I'm talking about. During my Marxism series, I sort of took Desmos to its limit, which is really what led to the project that I'm showing you here. And I used it to explore Morishima's completion of Marx's reproduction schema. You can find that by clicking this link here. I'll include a link to this file in the description or something. But I can go to it now here through this. Here it is. You've seen this before if you've watched my videos. If you haven't, here it is. This is a pretty comprehensive dynamical model, or a solution to a dynamical model. But you can adjust the parameters and see different solutions. It's an economic model, and you've got different sliders for basic parameters. Really, it's got about 5: the rate of exploitation, rate of reinvestment, and all that. And you can see I've inserted educational kind of comments to sort of communicate to somebody using this app what's going on with it. But then you can already see some limitations. The first limitation is the fact that there's no way to hide stuff like this. At least as far as I can tell, I can do this. I can hide them here, but a regular user doesn't really need to see this stuff, and there's really no way to sort of not have it here. Same thing with these. So there's just too much information. There's a lot of intimidating things that will scare users away. There's no way to really kind of have fancy text here in these comments. Like this should be mathematically expressed, but it's just, I can't do that. So there's a lot of limitations just in terms of the presentation. If I'm trying to package something like this to present to people as an educational exploratory tool, my ability to do that is limited to effectively what you see here. I think this model here that I've built is really Desmos taken to its absolute limit. And so I felt those limits pretty keenly, but the limits aren't just presentational. There's some more dire kind of limits that really made me feel unable to do what I needed to do in terms of my research. So let's talk about those. This is the stuff I said already. So Morishima's reproduction schema model is a system, in its first instance, it's expressed as a system of differential equations, or difference equations, but they're basically the same. So I'll call models like these differential models, where basically you just state the relationship in terms of how different quantities change with respect to one another. And that's often something that you can do very naturally, and then you want to see what the results of those models are. You want to see the model play out based on those rules that you created. And you can do that in Desmos for this specific model only because it has a closed form analytical solution. But that's not generally the case, or at the very least, it's generally not going to be. It's generally not worth the time and effort to even try to find an analytical solution. A lot of differential equations or systems of differential equations don't have closed form solutions, and even less often are those closed form solutions worth actually pursuing. Most of the time, in a physics application or otherwise, the better option is to simply simulate the solution to the differential equations numerically. Of course, I don't want to downplay it. There are reasons to try to find analytical solutions to differential equations. You want to prove things about them. But if you just want to see what it looks like, if you just want to see what happens, numerical solutions are really the way to go. And what I mean by that is have a computer do something like Euler's method, or Runge-Kutta, or what have you, backwards differentiation, whatever. There's all sorts of methods to simulate the evolution of a system expressed as a system of differential equations. And Desmos, of course, doesn't have a way to do that because it's just a graphing calculator. So this is one of those ways, one of the major limitations of Desmos is that if you want to use it as a tool for exploring models, and your model is expressed as a system of differential equations, as Morishima's is, and if, unlike Morishima's, those differential equations don't have easy to write down closed form solutions, you just can't use Desmos to look at those solutions at all. And then another major limitation is agent-based models. So another modeling technique that's often used, and it's becoming very popular, is agent-based modelings, where you have these agents that behave and interact with each other according to rules. And then you just write code that has the agents kind of spawned in, and then the agents sort of interact with each other according to those rules. And from those rules, you get to observe macro level emergent phenomena as a direct consequence of the micro level interaction rules. And so agent-based modeling is extremely cool. And there's a lot of really cool models that people like Cockshot and Cottrell and other people have created that you just can't explore in Desmos, because Desmos doesn't let you write code. It's a graphing calculator. So again, the limitation of Desmos is that it's not a programming language. It's just a graphing calculator. It graphs the functions you give it. And I want it to graph more than that. I want it to do more than that, but I can't. So, the goals of Overseer are as follows. I wanted to create a platform which allows me to create, explore, and communicate models of any kind. Whatever I want to do with the computer, I want to be able to do something Desmos-like. I want to be able to make a Desmos interface immediately. And it's not just for the sake of communication. It's not even just for the sake of creating. It's also an exploratory tool. It's all three of these. So the first goal of Overseer is to minimize the friction between having an idea and executing on that idea with your code. And Python is the perfect language for that, because Python is a very simple language to learn. It's very pseudocode-like. Everybody loves Python. And I want to minimize the amount of technical skills that I have to go read a manual for just to execute on my idea. So, a standardized way of building models in general is sort of what I want here. Explore. I want to, through the software, I want to be able to engage with my model dialectically. It should be easy to explore the model graphically, and I should be able to make changes to the model, to the code, and instantly see the results. I want to be able to incrementally build my model in a reactive manner by seeing what's happening and reacting to what's happening. I want to be able to try something, see that it doesn't work, and then iterate based on what the results are. So the dialectic of exploration is not just for the sake, these two, create and explore, are very tied in together. I want to be able to build in an interactive manner that's fun. And then finally, communication is equally weighted here. When I'm finished building the model, I want to be able to create out of it a professional-looking educational tool that I can show to others. I want to be able to hand them just like a little app and say, hey, use this, and you can learn about the model. You can explore the model with me, with whatever paper I'm writing or whatever. I want them to be able to easily see what they need to see the information, the extra text that I want them to see. And I also want them to not be getting intimidated by seeing too much, right? Because we had that issue with Desmos showing too much. Desmos is pretty good as a communication tool, and in this sense, that this is really the way in which Overseer really carries that flame forward, I guess, right? So those are the goals of Overseer. This is really Overseer's mission statement. Maybe such a piece of software already exists, maybe it doesn't. For better or worse, I took matters into my own hands, and this was my first major software project, and honestly, I really don't consider myself to be a software designer, and I'm not sure I ever will. I really consider myself still to be a theorist. I needed a specific tool for the work that I was doing, and Overseer is that tool, and I don't see myself becoming motivated enough to do something like this again. So I do think this is the only project like this that I'll ever do. Anyway, it's open source. You can find a link to the GitHub page for it here. I've got it open already, so we can go to it. Here it is. In this video, I'm going to show off some of its features to you guys, and I'm also going to kind of show you how to get started quickly building models with it. I'm not going to show off every feature that it has. It actually has too many for that, and I'm also not intending to show you exactly how to use all of the advanced features. I'm going to show you how to use it in a basic way, and I'm going to advertise some of its advanced features, but I'm not going to comprehensively list out how every little thing works. However, you can find such a thing right here by clicking this link, or on the GitHub page. If you go to the GitHub page, and then you scroll down to user guide and documentation, you'll find a link to this readthedocs.io page, which will take you here, where I do have this took a very long time to write. A pretty exhaustive wiki page on how to use Overseer, and you can see it even has videos explaining how to do everything. And in fact, this tutorial here, this quick start tutorial, is basically what I'm going to do in this video. So the focus of this video isn't going to be on walking you through the installation of Overseer. If you do need help with that, I'll probably include a little appendix video that's unlisted in the video description. explain, walking you through that, but I don't want to dwell on those details. Rather, I want this video to function as a tutorial for using Overseer to build your own models, and as a feature demonstration, basically. So all I'll say about installation besides that is that currently the best method of installation is probably just cloning the repo yourself and installing it manually using pip. I did spend quite a bit of time trying to make dedicated installers for Windows and Mac OS that would make the process more streamlined. But the thing is, every time I make an update, I have to redo that process, and it's just the pace of updates is just too fast for that right now. And so it's a losing battle to try to keep those updated. They do exist, but if you download it, it will give you an out-of-date version that is buggier and performs worse. So I highly recommend just cloning the repo. If you use Python, you know what it means to pip install something, and it's basically just that, except you're pip installing the folder that you download from GitHub, basically. So it's really not hard, and I don't think, if you know what you're doing with Python, even a tiny bit, I don't think you'll have much trouble with it. So yeah, without further ado, let's just jump into Overseer, and I'll show you how it works, and we'll build a couple models together. So when you first boot up Overseer, you should see something like this. A model should automatically load because Overseer comes packaged with a bunch of example models, which are basically just the models that I make myself for research. I just kind of include them as open source free stuff that you can play around with. This one is Ian Wright's cross-dual disequilibrium model, or specifically my version of it that I used for that paper that I mentioned I wrote earlier. You got all sorts of controls here that can do all sorts of things. And you've got a graph here, and you can see, it looks a lot like Desmos, and that's I'm not going to keep saying that over and over again. How do you use this? Well, first of all, to move around, you can just click and drag, and you can see that will move around on the screen. That's left click and drag, by the way. If you right click and drag, then you will actually magnify. So if I right click and then move right, then you can see I zoom in horizontally. And if I right-click and then drag up, I'll zoom in vertically, and of course diagonally will do both. So that's really handy. That's something Desmos doesn't have, but I like it a lot. That's built into Matplotlib, actually, the ability to do that. So between the left-click to move to pan and then the right-click to magnify, it's very convenient. You might have noticed if I click, it'll actually snap to the nearest curve and show you the exact coordinate, just like Desmos. But if you want it to actually drag around like Desmos, you can either click this button here, and then moving the mouse instead of panning will actually move the blip around, or you can press Control P to toggle between them. So I could go on and on about how the controls work, what all the buttons do, but I think that's not really the way that you should introduce your software. I think the way that I'm going to introduce and my software and sell you on it is to just quickly preview some of the capabilities that it has, and the best way to preview those capabilities is to show off some of the example models that it comes with. So maybe the one that I'll start with here is this Epstein civil violence model, not that Epstein. So you can open that up just by clicking it in the demos, and I'll talk about what a demo is shortly. But you can see it has two plots that open up at once, but this is a little bit of a drag, so let me just close it. So what you have here is a 2D grid that the agents exist on. Now, you've got two kinds of agents. It's an agent-based model, cops and citizens. So the cops are triangles, and the citizens are circles. And I think it's easier to understand if you disable movement of the agents to start. So basically what you have here is this is a model of civil violence. The agents have a perceived degree of legitimacy of the state that they exist under. Here it's 0.8. And that influences, the higher this is, the lower of a chance that they have of going active, which is a euphemism for rebellion. And when they obviously rebel, they turn red. When they turn red, when they go active, other citizens around them have an increased chance of going active because these citizens are making a mental calculation of how likely they are to be arrested at a given moment if they go active, and that calculation is based on two things. It's based on how many cops they see around them, and also how many other active agents they see around them, because the more active agents there are, in addition to themselves, the lower of a chance they themselves have of getting arrested. And so that's why you can see this kind of wildfire-like behavior where this rebellion starts and then immediately spreads out, and so it's really fun to watch. And the cops, of course, eventually arrest everybody, and then they go gray, and they can't go act. That makes them unable to go active again for a certain amount of time, depending on the jail sentence, which you can control via right here, which is 30 right now, 30 time steps. So let me just explain what the controls are, or explain how you can understand what these controls are. You can see that each of these controls here has a question mark box by it, and if you just hover over the question mark box or click it, it'll show you what each of these parameters actually controls in the simulation. So you can see W here is the width of the 2D grid. So it'll make a bigger grid if I change this number. L here is the perceived legitimacy of the existing state. So lower values of this increase the chance that a citizen will go active. And likewise. And so this is one of the main tools that Overseer has for allowing you to build models that don't just allow you to explore them, but also allow you to communicate them to others, which was a big important thing. When I was making Overseer, I wanted to allow you to make models not just for yourselves, but that you could communicate to others with. So that's one thing, and you can see, one thing that this is showing off is the different kinds of plots that are available. So if I restart this, I've got a dynamic pie chart here. That's pretty fun. That you can see kind of the proportion of the population that is in different states at a given moment. So so maybe the next one to look at would be the Morishima model. So here is the same Morishima disproportionality reinvestment model that I go over in my videos. So if you watch those videos, you should be pretty familiar with what you see here. It's the same thing that I just showed in Desmos earlier. But there's a few new things here. There's a few new things here that I couldn't have done in Desmos. You can see here that there's a simulation type option here, and you can choose between matrix exponential and analytic. If I chose analytic, then it would basically be just like Desmos. At that point, I'm giving it the solution. I'm giving it those closed form solution functions, f of x equals, and I'm just having it make all the plots. But if you choose matrix exponential, that's what allows it to actually dynamically render like this, because what it's doing is it's not just plotting the solution, it's actively solving it using this technique of repeated matrix multiplication. And that allows you to see the simulation evolving. And since you can control the simulation as it's evolving, you can intervene and you can enforce things and you can add additional complications and rules. And so there's a few controls here that just I couldn't have had before with Overseer. In particular, you can choose to enforce a full employment ceiling and have a fixed population size. So here, I've got a population of 180, and then a reproduction rate of 0.02. So basically, each period, the employed-only population will grow at a rate of 0.02. If they're not employed, they don't get money. They don't get any wages, and so they can't afford to have children. And so only the employed population is able to grow. And then actually, S here is an attrition rate for the unemployed. So if the proportion, this is the proportion of workers that will die off each period if they're unemployed. And so this usually doesn't actually matter unless you enforce this full employment ceiling. And so if I do that, then you can see I get very different dynamics. And so the intervention can produce all sorts of crazy, interesting results. I can also enforce a non-negative value output. I had to talk about that a lot. And so you can see, there's all sorts of more interesting things that you can do here that you just couldn't do in a modeling toolkit like Desmos. So, that's an example of that. So just some quick rundown of other kind of plots that you can see. Here's a example of a 3D plot of a curve that's evolving over time. Pretty cool. Here's another. You can make surfaces in 3D. So here's an example of a 3D surface evolution. No modeling demo would be complete without our boids. So here you've got a flocking model in which these sort of represent birds that kind of end up converging to sort of patterns and kind of elegant behaviors with respect to one another. And much more. There's lots and lots of plot types. I haven't added every single plot type that Matplotlib is capable of generating, but I have added quite a few, and the system in place makes it easy to add new ones as I need them. So one of the ways that I've been building Overseer is I've been reading lots of papers and then just building the models in those papers in Overseer and just kind of trying to say to myself, can I make every plot that I see in this paper? And if I can't, then I'll add the feature. And so that's how I've been sort of prioritizing what to add and what not to add so far. So hopefully I've convinced you now of the power of Overseer. What I'd like to do now is show you how to build your own models in it. So before we do that, I should probably give you a sense of where these example models and where the models you'll build are found. You can control that yourself in the settings. If you go to Application Settings, you'll see User Models Directory and User Logs Directory. These are the files that really belong to you. And when you first boot up Overseer, it will create these folders for you. It'll target a user documents folder. So it'll, both Mac OS and Windows have a documents folder, and it'll find that folder and it'll create a folder called Overseer on it, or inside of it. And then it'll create a models folder and it'll create a logs folder. And if it's finding if it found that it had to create one of these, the models folder for you specifically, it'll dump all of the example models in there for you. And so that's where things are by default. And you can change it if you want. It does require a restart, but you can change this yourself. And so that's where you'll find things. But let's go ahead and make a new model. So to make a new model, we go to Model Settings. And so here are all of the models that we have already. So to make a new model, we just go ahead and give it a name. So we want to make a name for it. So I'll call it YouTube Demo Model. Probably don't need the word model since it's already under models, but whatever. So I've written this in, and so now we just click Create Directory. And so you can see YouTube Demo Model is now right here. And it says Model YouTube Demo Model created, and then it gives you some next steps. I'm not going to read these off because I'm going to show you it. So if you open up your user models folder inside of your documents folder, you will see that by clicking this Create Directory button, that's literally what it did. It created a YouTube Demo Model folder, which has some basic starter stuff in it for you. The next thing that we want to do is open up this folder in your code editor, or open up the relative files in your preferred code editor. And you can set that code editor in the application settings. You can select the preferred editor IDE. And I've given some basic options here. I'm going to select NeoVim. And if it is a terminal-based editor, you want to select kind of a terminal opening command for it as well. So I'm going to pick Kitty. So let me go ahead and apply that. And then I will go ahead and say Open an Editor, and you'll see it just opens it up like that. So you don't even have to know, where it is exactly if you don't want to. Keep in mind, by the way, that it's perfectly okay to just open up the folder in your preferred text editor just in the normal way too. You can do that. What the next step is however you feel like doing it in whatever preferred text editor that you want to use. Go ahead and open up the simulation.py file inside of the simulation folder of the model you created. That's the next step. It'll just open it up for you. So let me go ahead and open this up in a different screen and give you a sense of what we have here. So you can see we're in a specific file called simulation.py, but if you look at the file tree, you'll see that there are several files. There's two folders. One of them is called data and one of them is called simulation. The simulation folder is really where you'll be writing your code, and even more specifically, your code is going to go inside of the simulation.py file for the most part. You can make other files, but at the end of the day, simulation.py is where Overseer looks to find the kind of overall function that it's running in order to run your simulation, and by default that gets named get trajectories. So let's say, for starters, we just want to create we just want to use Overseer as a graphing calculator. We just want to plot, let's say, f of x equals sine of x in Overseer. How do we do that? Well, it requires a little bit more thinking than in Desmos, but not a whole lot. What we're going to do is we're going to just create the data set of sine of x along a whole bunch of specific x-axis points. So the first thing I'm going to do is I'm going to say x data equals np, so that you can see that it already pre-imported NumPy, and it also installs NumPy if you don't have it when you install Overseer, .linspace. So now obviously I am expecting the user to know just a little bit of Python in advance, and if you know a little bit of NumPy, that'll help too. If you don't, you'll learn. But what linspace does is it creates basically, it creates for you a set of points that just basically are equal distance between two bounds. So maybe I want to go from -5 to 5, and I want 300 points. So that creates your x data. And the cool thing about NumPy arrays, they're not actually lists, they're NumPy arrays, is that you can just feed the x data directly into NumPy functions. So I'll say sine data equals np.sine of x data. So I got my x data, I've got my sine data. And so now that we have this, what you need to prepare for Overseer is you need to prepare a dictionary of the data that Overseer needs to look at in order to plot your data. So I'll say data. So I'll call it export data, and I'll make it a Python dictionary. And what this dictionary needs to consist of is key value pairs where the keys are strings, and the values are the data itself. So I'll say x data. I'll just call it x, and I'll assign that to x data. And I'll also create another key value pair. I cannot type sign, and I'll call it sign data. And then you can simply return export data, and that's it. That's actually all you need to plot sine of x. In fact, it was so easy. Let me just go ahead and also, while I'm at it, create cosine, because why not? Okay, so this is the most basic possible model you could build in Overseer. This is the code right here. So how do I, from this, run this simulation, quote unquote, and see the results in Overseer? Well, once you've got your YouTube demo model, what you're going to want to do is go to plot settings and create the plots. So plots are split into categories. And what I mean by that is if you go if we go to our Ian Wright model here, you can see that if I go to plot controls, there's a drop down here where I can select all sorts of categories. These are all plot categories. So if I go to output supply and demand, then I get a whole bunch of plots that have to do with supply and demand. And I can check them on and off, right? I can turn off any of them that I want, and I can turn on the ones I don't want. So, so you've got categories, and then you've got checkable plots within those categories. So for my YouTube demo model, I want to first create a category, and I'm just going to call that category everything because I'm not going to make more than one of them. And there we go. I've created the category. That's all you really need to do. And then the next thing I'm going to do is create a plot inside of that category. So I'm going to click the plus plot button, and that will create a new plot. And so here is the plot settings, and you can select the plot type. Here are the options here. My plot is just a curve, so I'm not going to change this. I'm going to make sure to check the initially toggled box, and then I'm going to give it a name, and I'm going to call it sine. And then you can see that you've got all these options, but only one of them has a star here, because only trajectory key is the only necessary input is trajectory key. And so what this trajectory key is referring to is the key in the key value pair of the dictionary that you are returning. So in this case, that's the purpose of this string called sine here, is that Overseer is expecting to get this dictionary with all of the data inside of it, and then you point it to the data that you want by telling it how what plots it's going to create and where it's and what keys it's going to look to in the creation of that plot. So I'm telling it right here that you need to look for the sine trajectory key to plot the y-axis, and I'm also going to give it the x key for the x-axis, and then everything else can be left alone. I'm going to go ahead and assign it a label and a color. So the label is what appears in the legend. So I'll call this sine, and then maybe I'll make it red. So you can just type the word red, and you can see it appears as red. And then we'll go ahead and do the same thing for cosine. Why not? Maybe we'll make it blue. And there we go. So I'll go ahead and click apply on that, and that will create create the plots for the model. And now there's one more step. I've created my model. I've created my plots. Now we need to create a demo. So what is a demo? A demo is short for demonstration, obviously, and it's basically something that you're interested in showing somebody using the model that you created. The difference between a model and a demo is the idea that there might be multiple things that you want to show the user within a specific model. And so you might want to have like multiple demos to choose from to showcase different aspects of a model. And so there are multiple things you might want to demonstrate using a model, and so there are models and demos, and those things are separate from each other. So, but you still have to have at least one demo showcasing your model, and so we need to create that. So I want to click plus demo, and it'll have a new demo. And then what I can do is I can give it a display name, like YouTube example. You can give it a description if you want. We'll leave that blank, and then I'll select as the simulation model YouTube demo model. And you can see that it defaults to the simulation function, get trajectories, that was automatically created, but you could change it to a different one if you wanted to. And then let's not worry about these other options here for now. And that's all you need to do. So we'll go ahead and click apply, and then we'll click save to close it. Save just does the same thing as apply, but it closes at the same time, so I technically saved twice. And that's it. We've created our model and we're ready to run it. So if we go to demos here, you can see that YouTube example appears. And if I load that demo and cross our fingers, you can see, here we go. I do see a red line for sine. It's not exactly the right dimensions, but we can zoom out. And here it is. Here's our nice, pretty sine function. And that's it. So now we have our controls, and you can check sine on and off. We can check cosine on and off. So the last thing you might want to do with respect to the demo is we want to make it so that the user doesn't have to like zoom out in order to find the functions looking like this. And so how do we make sure that this is the default view when we open it up? It's actually not the save view as default button. I'll talk about what that is in a little bit. What you want to do actually is go to view and then say save current axis settings. And it'll say down here, current overall view saved as demo default. So this save view as default is referring to specifically the category. So if you change categories and then change back to this category and you've clicked this button in this view, it'll default to this view. So we can do that too. That's a good idea. But if you want it to load into this view when you first open up the demo, you need to save this. And those are different view settings. So maybe the wording needs to be changed to something. But yeah, that's that. So now every time we load this demo, it'll just look like this. It'll be focused on -5 to 5, and it'll look like this. So that's a start. First of all, how do we change and reload the demo? How do I engage in that dialectic that I was describing, where you kind of iterate on your code? So let's say that I want to change like the frequency of the sine function, just as a very small example. So we'll go back to the code here, and obviously the frequency is controlled within the argument to sine. So what if I just put like 2 times x data? So that's all I've done. I'm taking all of the x data and multiplying it by 2 now. If I save that, and then I go back to Overseer, all you have to do is press F7, and you can see that the frequency has changed. So it's that simple. Whenever you press F7, you could also alternatively go to simulation and say refresh simulation files, or refresh and restart simulation. It'll just reload your code and run it again. And so here we go. Now I see sine differently. But that's a little bit manual, right? What if we want to make it so that I can adjust with a slider, like in Desmos, the frequency of the sine function or the cosine function? Well, for that, we need to mess with our parameters. So what we want to do is we want to go to settings and then parameter settings. And obviously it's empty right now. And I want to add a parameter that controls the frequency of my sine and cosine functions. So I'll say plus parameter, and it says new parameter float. And so it'll default to a float. So I'll give it a name. I'll call it maybe B. Maybe I'll have 2 parameters, one for the amplitude of the wave and one for the frequency. So I'll create 2 parameters. I'll call this one A, and I'll call this one B. I'll make them both floats. And then I'll have, and then it's good to, I think it's standard practice in Overseer, I would say, to assign a default value wherever possible. It's nice to have default values assigned so that that Overseer doesn't get confused. You don't have to assign defaults, but it's good practice. So let's go ahead and make them both default to 1. You can see that there's a bit of a red warning here because it doesn't like the fact that you have a default value for A but not for B, and B is underneath A. So if you just click this shift defaults down button, if there is something that basically if there is a variable or a parameter that doesn't have a default value, you need to make sure that it appears before all of the ones that do have defaults. The default parameters, the parameters with defaults should always appear underneath, and you can always click this button to resort them, or this up and down to kind of arrange them yourself. Anyway, but we are going to have them both having default values, and so that's 1 for both of them. And yeah, so there it is. We've created 2 parameters. I'll click apply here. And now let's go back to the code and look at what we just did. So if you look at the file tree here, you can see that there's a parameters.py file. And if we open up that file now, you can see that there is now a class called params, and you can see my A and B here inside of that class. So this is a data class. And so a data class is just kind of a container that contains, various things for you. And so it's just a structure, it's just a data structure. And here it is. So now, inside of the simulation file, you can see that getTrajectories always takes an instance of a parameter's data class as its first argument. And so that is where we refer to those values. So for what I can do is I can just say a equals params.a, b equals params.b, and now I have a and b here, and I can use them wherever I want. So I can go ahead and say a times x data, or maybe b times x data, maybe in both sine and cosine, and then I'll go ahead and take the whole function and I'll multiply it by sine and cosine respectively. So again, a is the amplitude, b is the frequency, and I'm just kind of applying those where that is appropriate. And that's it. So now I'm using my parameters. If I reload the simulation with F7, nothing will happen because a and b are both 1 right now. So what we want to do now is we want to create controls. Our simulation controls tab is very boring right now. It doesn't have anything in it. So that's separate. We want to go to settings now and then go to control panel settings. And now we want to add a control. And so if I say add a control, you can see it defaulted to a because a is just the first parameter in the list. You have different control types to choose from. The one that we want for numbers, generally the one that you want to pick is entry block. And then this label is what will, label the control. It's what will show up to the user. And so I'll have it default to A. And you might notice that these dollar signs here are latex math mode script, and you can use that if you want. You can go ahead and say A equals, and I'm forgetting myself here actually. There's something, you can add the parameters manually, but even cooler, let's go ahead and close without saving and reopen. What you can actually do is you can just simply say initialize from parameters. You've got a button here and you can click it, and it'll take you through basically a wizard that will automatically create a controls tab for you. And so here we can see it already has the controls. You definitely need to review what it creates for you. It's doing its best, but it's not always going to do what you've expected to. In particular, I would like this A and B to appear in math mode and look like nice latex font. I'd also like to make it so that the range of A is not from 0 to 1. That's pretty boring. I would like it to go from maybe 1 to 5, let's say. And then I'd also like B to go from maybe also 1 to 5. So definitely change the range min and range max. When it finds a float parameter, it will just kind of default to 0 to 1. And so you almost always want to change that. So we've created our controls. And so now if we just click apply, you can see they automatically appear. Here we go. We already have some controls in the simulation controls tab. I'll go ahead and say save. And so it should be the case now that if I just move this slider over a bit, look at that. The frequency changes automatically. It's not as instantly responsive as Desmos is. It doesn't happen as you change it, but it does happen immediately, and so it's pretty responsive. So the last thing I'll say about the controls that you can create is in these control panel settings, as well as the plot settings. First of all, you can just drag things around. So if I drag A underneath B, you got to be a little careful, and then hit apply. You can see that A and B have flipped. So you can pretty easily drag rows and columns around. Another thing to mention is that controls do appear in rows. So you can, if you want the next control that you create to happen underneath A and B, you would have to add a new row and then make sure to create it under that row. If you create a new plus control, the control will happen inside of the row that you have selected, or inside of the same row as the control that you have selected. But the last thing I'll mention is that if you want this tooltip to say anything, you just have to add it here. So maybe for A, we'll say controls the amplitude of the waves, and then I'll say here controls the frequency of the waves. And you can insert LaTeX font here too. You can go into math mode if you want. And if we click save and then click this, you can see it tells the reader, it tells the user of your model what these controls actually do, which is great. You can do the same thing in the plot controls for the categories as well. Right now it just says no notes, but if I opened up the tab, anything I put in here, like if I said here is everything, and then click save, and then I click this, it would say here is everything. So again, these question mark boxes are just kind of everywhere, and so that allows you to make your model explain itself to the user just through their own play. with your model. That you don't have to you don't have to put everything in some kind of paper somewhere. You can actually have the information inside of the application itself, which I think is really fun. We're sort of at Desmos levels of complexity, but you already saw that Overseer can do more than that. So maybe the next thing we should do is, right now, it just sort of, makes the graph immediately appear. So how would we make it animate? I want to see sine sort of evolve over time rather than just appear all at once. I want to see it look like a real simulation that is being run. So how do we do that? Well, if we go back to our getTrajectories function, you can see that right now we are returning the export data all at once. We're just putting everything out there all at once. So we need to do something different than that. So basically, this is a lesser known feature of Python that isn't used as much. But there is this return keyword which just simply returns the value of a function. There's also another kind of keyword that you can choose to use instead when you're defining a function called yield. So what the yield keyword does in Python is it takes your function and it turns it into something called a generator, which effectively makes it something that can be looped over. So basically the idea is, let me just kind of make a very simple example. Yield. So right here, if I said return dog, and then I said return cat, and then if I said example yield or print, I'm not going to run it, but print example yield twice. You can see the cat is grayed out here because my programming assistant or whatever knows that it's just going to return dog every time, because the first time you encounter dog gets spat out, and it's just going to do that every single time I call example yield. But if I yield instead, at that point I can't actually just call the function twice like this. But what I can do is I can say generator equals example yield, and what this does is it creates a loopable object. And then what I can do is I can make a for loop that kind of loops over it. I can say for output in example in generator print out. And so what this will do is it'll effectively loop over this function like it's a list. And the way that works is it'll simply run the function until it encounters a yield, and then that will become out, and then it'll print that. And then the next time that it runs again, it'll continue where the last yield left off. So it'll run this line next, and then it'll print cat. And so basically that's the idea, is that it'll continue where it left off until it encounters another yield, and then it'll just continue like that until there's nothing left to yield. And so this is absolutely perfect for us, because what this allows us to do is use the getTrajectories function to, instead of returning an output all at once, return progress incrementally as it does whatever it's doing overall. And so Overseer will notice that you're yielding instead, and it'll attempt to loop over and show the results on your screen whenever it gets something new yielded. So let's go ahead and convert this overall system into that. So as you can see here, I've removed everything, and so we're just going to start over. So whereas before, so what would change here? So first of all, if I'm going to be reporting partial data, then I don't want to define the X data all at once like this. So instead of doing what I'm doing here, I'm actually just going to say X. I'm not going to go ahead and say X data. X is faster to write. So I'm just going to say X equals np.array, and we're just going to have it have a single value in it. We'll have it be just the left end of the data set and nothing more. And what I'm going to do is I'm going to have a for loop. I'm going to say for dummy variable in range 300. And what I'm going to do is I'm going to basically redo all of this stuff, but using X. I'm going to rename these variables. I'm just replacing X data with X because it's faster. So it's going to basically look like this, except instead of this on its own is almost complete. The only thing I need to do now is I need to increase the size of the data set that I'm looking over. So what I can say is x equals np.append x with the last thing in x plus, well, we need to know how much of an increment we need to add, so that it kind of ends up going from -5 to 5 in the span of 300. So let me go ahead and just kind of open up a calculator real fast. And if I do that, I can just say, like, so -5 to 5 is an interval of 10. Dividing 10 into 300 equally spaced chunks is basically 0.33. So it's not going to be perfect, but I think if I just say 0.03 here, that will just basically create a new value inside of this array that is, after this it'll be minus 4.97, and then it'll be 4.94, and then it'll continue like that. And then, we're doing this at the end, so then the next time that this loop happens, we'll get the sine data and the cosine data on a slightly wider data set, and then we can yield it. In fact, what we can do is we can put the yield function right here. So what this will do is it will take the export data with the current x data, and then it'll yield it, and then after, once it's done yielding, it'll append the value, and then it'll do it again. And so this is really kind of what the more sophisticated version of it would look like in Overseer if you want it to animate and show you results in real time. So let's go ahead and save this, and then we'll go back here and run it again. And you can see, there it is. It animates. Simple as that. Well, maybe not the simplest thing, but it's certainly not that complicated either, right? I mean, this is, once you get the hang of it, once you get the hang of how yield works, this really ends up feeling pretty natural. And the really cool thing about it is that you can, in the context of whatever model you're building, you can yield whatever you want whenever you want. So it's really up to you when you yield. It doesn't have to be in a consistent place. You can yield whatever whenever. And yeah, so that's how you make things animate. That's how you make Overseer actually run a simulation in a more real sense. Now, so what I'd like to talk about next here is the efficiency of this and how you can really maximize Overseer's performance with some standard practices. So I should preface this by saying, like, if you're satisfied with how your simulation is performing, which looks pretty good right now, admittedly we're not doing very much, then you don't really need to listen to what I'm about to say. But if you want to use Overseer to its fullest, you should. Because what we're doing right now is a little bit inefficient in some ways. For example, the fact that I am remaking my X array every single iteration of this loop with this np.append function, that is what it's doing. I'm remaking the entire X array, adding this little point to the end, and then sending the entire data set of all of the points to Overseer. So there's kind of two inefficiencies there. The first inefficiency is the fact that I'm remaking the entire array from scratch every step of this for loop. And then the second inefficiency is in the fact that I'm sending all of that data, which is a lot of redundancy, right? Like every single time this loop finishes, I'm yielding the data points that include -5, and then all of the data. I'm just sending the same data repeatedly to Overseer. And so both of these are dealt with in the same way. You might have noticed up here, we're importing some things from Overseer itself. These special replace, extend, and append data classes. You should think about these replace, extend, and append data classes as envelopes, like labeled envelopes that you can choose to put your data inside of before sending it to Overseer. And then Overseer, from the envelope name, will know what to do with it. And so right now, it looks like we're sending the entire data set. We're sending this entire NumPy array that represents all the sign data to Overseer all at once. What I want to do instead is I want to just send a single new point at a time. I don't want to send the entire data. So in fact, what I want to do is I just want to say x equals -5. And then instead of this np.append stuff, I just want to say, x plus equals 0.03. I don't want to have to, evaluate a whole data set all at once. And so basically, this calling the signed data at this point isn't really appropriate. X is just a float now. And so this value, NumPy is going to realize x is just a float, and it's just going to return a single number as well. So we're better off calling this sine val and cosine val, like val for value. But we have to tell Overseer what to do with this single float number. We can't just send the single number on its own. And so that's where our envelopes come in. So we want to basically put this sign val inside of an append envelope. So this append data class is what we're importing from our Overseer data classes. And we want to do the same thing for x. And that's it. So now we're only sending a single number, but we're wrapping it in this append value. And what's going to happen is that Overseer is going to be receiving these numbers, and it's going to see this append, and it's going to realize, oh, okay, I'm going to interpret this as the next value in this time series called sign. And I'm going to actively maintain this overall data trajectory. And so now I'm only sending a single piece of data at a time. I'm not doing any extra computation. And that's it. If I go back to Overseer and run this, and that's it. If I go back, and that's it. If I go back to Overseer and run this, there's no difference. You shouldn't notice anything different. But now there is absolutely no efficiency loss. Overseer is perfectly efficient now. Now, I realize some of you that are familiar with matplotlib might be doubting what I said there just now about efficiency, because there is a bottleneck implicit to the rendering of what you see here. Indeed, matplotlib cannot just update a plot with the next set of points. It has to just delete and remake all of this. There's no dynamic updating of an existing plot. That matplotlib just doesn't operate that way. And so that would seem to create a quadratic slowdown to this overall process. However, I believe that the way that Overseer handles all of this makes that irrelevant to the efficiency at which you can witness your simulation rendering. And I've made a diagram explaining that. If you don't care about this, this is kind of technical, but I think it's worth explaining a little bit about how Overseer works overall. So I've created a diagram here to just sort of explain how Overseer manages this. Remember, it's a Python program. And Python has this thing associated with it called the global interpreter lock. This makes it so that Python multi-threading isn't actually really possible. Python runs on basically a single core at most of your any Python application that you make will run on a single core at best. It can't do true multi-threading like a more robust programming language like C++ can. However, you still have a multiprocessing library that you can use to split off and run other Python processes. And there's also a kind of pseudo-threading system that it has as well. And I use both of these here when running your simulation. So this is a diagram of that. So first of all, you've got the main Overseer process. And this main Overseer process has two threads. Now remember, these aren't true threads. This is just basically time sharing. Like this gets some steps, and then this gets some steps, and then this gets some steps, and so forth. But that's all that's really needed here. Now that said, your simulation itself does happen in a separate process. So basically, when you hit start simulation, a separate Python process is created whose job is to iterate over your simulation function, just repeatedly like loop over, receive those yields, and then deposit the results that it gets from those yields into a queue. So that's what happens there. Then there is a bridge worker, is what I call it, which is a thread in which basically repeatedly the queue is drained, the queue that the results are put in, and then the appends are processed and all of that, and the actual time series are constructed. And then there's a separate thread in the main process in which on a timer, a separate timer, matplotlib is called on to just plot whatever is currently the results as the bridge worker has constructed them. And so overall, the runtime, you're redoing the entire plot every single time this animation timer goes off. However, the fact that this bridge worker is on a separate thread means that no matter how long matplotlib takes to render the current plot, the bridge worker is still doing its job, and so is your simulation, meaning that the results are being updated even if matplotlib takes a long time to render. And so the next time the animation timer goes off, even if matplotlib was a bottleneck in terms of taking a long time to render, the results will still be updated as if it didn't take that amount of time. And so the end result here is that at most matplotlib can only make the animation look choppier. It can't fundamentally slow down the rate at which you're seeing simulation results. In other words, Overseer's ability to show you the results of your simulation is fully linear time in the data that you're sending. It's perfectly efficient in that sense, I think. So that's kind of the overall architecture, and I'm pretty proud of that. So Overseer is actually very efficient, even though it's a Python program, and Python programs are notoriously inefficient. I do think that the system here works really well, and that Python is fully able to render your simulations as fast as you program them. So that's pretty cool. So if we go to the settings menu and we look at the different settings menus available, model settings we've talked about, parameter settings we've talked about, control panel settings, plot settings, demo settings, we've talked about all of those. Edit key bindings is self-explanatory. The only one we haven't mentioned is preset settings, so we should talk about that real fast. What is a preset? Well, a preset is, it's not really worth considering in this case, so let me jump to a different model that's more complicated. We'll jump to, like, Wright's cross-dual disequilibrium model. This one has a lot of parameter settings, as you can see. There's quite a few parameters here, quite a few, and sometimes you find something interesting, and you want to remember what the parameter settings were that were associated with that thing. And how do you do that? Well, you go to parameters, and then you can either say save changes to a current preset or save as new preset. So what a preset is it's a set of particular parameter settings at a given moment. And you can save your preset settings, and if I say save as new, you can see it also has an option to include access settings, and it also takes a description. So this is particularly useful, I think, for the sake of writing papers. So for example, let's say that you have a bunch of figures in your paper. You can include the presets for every single one of those figures to allow not only for the data to be open source, but you can allow for easily reproducible results. So you can go to figure like 7A or something, and this is, you know, not maybe depending on randomness and whatever you're doing, it might not be the exact figure that they see, but it will be very similar, right? You can go to like figure 2A, and you know you can give the reader of your paper the tools they need to not only see your results but reproduce them themselves through these parameter settings. So that's pretty cool. Another place where presets factor into Overseer is in the demo settings. So let me return to that real fast. You might have noticed this default preset here option when you're editing your demo settings. This is, you know, exactly what it sounds like. It's a default preset that for Overseer. The reason that we didn't need one for our YouTube example is, of course, because the parameter settings both had defaults set for them already. As long as everything has a default for it, you don't need to actually have an explicit preset created for it. But keep in mind that if I didn't have A set to 1, and I tried to restart my simulation, I would probably get a problem. Yeah, it would say simulation failed, unsupported operand. Yeah, it just doesn't understand what's going on because you haven't given it the settings necessary for every variable. So you would have to, so that's where a preset would come in, is you would have to set a, you can see that A here in the preset settings has a star by it, which is telling you that it is required because there's no default value found. Your simulation won't run unless you have a default value set for all of your parameter settings, or if you don't have a default value set for all your parameter settings, you need to have a preset that defines what those values are supposed to be, or else Overseer won't know what to do. So that's why I consider it to be best practice to always give as many variables, if not all of them that you can, a default setting so that you don't run into any issues with that. So, you know, let's say that I want to either analyze this data more closely with a different tool or just save it for later. What you can do is you can go to results and you can say save current results, and you can say cool results, and then you can say save. And then what you can do is, like, you know, if I go to like 54 or something, wow, that's crazy. You can go to results and you can say load results, and you can just immediately see them. It won't run the simulation, it will just load up all of those results instantly. So you can, this is a way to save the data, not the simulation. And the cool thing about this is that the data is portable. So if I go to the simulation folder and we look, you'll see saved results. And you can see that the cool results were saved as an NPZ file. NPZ is a NumPy archiving tool, and so this can be so this is just basically like a zipped folder of your results that you can take with you to whatever other data analysis platforms that you want, and you can analyze the data. You can analyze the data wherever you want. You can do whatever you want with the data. That data is yours, and it's stored right here for easy reference. So that's pretty cool too. And then the last thing in terms of like saving and creating stuff is sometimes you want to save a picture. Now, before you save a picture, I would highly recommend checking off this transparent background. That'll make the background look a little worse, and not make it look like it doesn't really fit into Overseer. However, if you save the transparent background, it will be transparent, and that can cause problems with whatever paper you're inserting your figures into. So you save the transparent background, and then we can click save, and then I don't really need to say much more. It'll save the picture. So that's all the ways that you can kind of save your results as you do your own exploration and building of your model. So a few other kind of basic things that I think everybody that's getting started with Overseer should know about is, first of all, you might have noticed that you have to, in the plot, if you look at plot settings, I had to specify X as the trajectory key for the X-axis, but the only one that actually got a star is the overall trajectory key. And the reason for that is that you can specify, instead of using X here, if I just called this T for time or something like that, then you can actually remove X entirely from both of these. You don't have to even specify it. And the reason for that, and it just works. And the reason for that is because Overseer will, by default, look for a key called T in order to use as your X-axis, because, kind of by default, T is time. Even if it's not time, you can still call it T. And that way, that makes it really easy to add new plots, because you don't even have to worry about, matching it with an X-axis. And Matplotlib is very picky about making sure that the dimensions are the same. Overseer is not. It'll actually just do its best. It'll truncate the data to the smallest dimension of both points. So if you say plot some Y data and it's got 205 points in it, and then the X data only has 200 points in it, it'll just plot the first 200 points of the Y data. So it'll by default look for that, and so you can use that, and it's really nice. It makes it a lot easier to add new plots. So just to also explain what the rest of these kind of envelopes do besides append. Append is the one that you're probably going to be using the most often. But replace is also very useful. Replace does what it sounds like. If you do have a whole data set, and for whatever reason you want to replace the entire data set on the update, then you would use replace. And that can be useful for things like, for example, that Weierstrass function demo that we saw earlier. If I jump to that, the entire function is updating every step here. And the way that I'm able to do that is by using the replace envelope to tell Overseer what to do. I'm actually probably not using the replace envelope there if I check. Yeah, I'm just returning the entire trajectory, because you might have noticed that replace is really just doing what was already being done at the beginning of this tutorial. So really, the replace envelope doesn't really need to be there. It's only there as like a verbose option, basically, to do what is already being done by the default if you don't bother with any of these. So I'm actually not using it here, but I could, and I should. That would be best practices, is to use it, even though I'm not doing that here because I made this before I added that. And extend, on the other hand, will do kind of what it sounds like too. So for example, if for some reason in a single time step, let's say that you have sort of several new data points to add to your series, you would just basically write extend instead, and it'll maintain it like append, but it'll interpret what it's seeing as like multiple new points to add to the time series at the same time. I've personally actually never found a use for extend, but it just seemed like a reasonable thing to have. And then update, which may or may not be generated actually by default in this file, is sort of a secret fourth thing. Update is kind of special because it sends information back to Overseer that gets processed in different places. So at present, the only real use for update is to, for example, if you have like a specific field in your control panel, like if you have information that you want to display in your control panel based on what's happened in the simulation, you can have that happen. Yeah, so as an example of the update method, I'm using update to update the random seed. So this is a simulation that I'm doing of a labor time economy with a group of students and a colleague of mine, and you can see that basically you've got this fixed seed here. So sometimes for debugging purposes, we want to kind of fix the random seed. And if you don't fix the seed, then every time you run it, the seed will be generated at random. And so if I restart the simulation, you can see that the seed changed on its own. And the way that the seed was able to change on its own was specifically using the update letter, the update thing. So you can look at the code for that yourself if you want to see how to use update. Update is really like an experimental kind of data class that I've created specifically just for this one control here. But you can use it. It works great. So yeah. So one more thing that I almost forgot to kind of share that I think is worth teaching in this video is how to use the logs pane. So you can see that you're viewing right now this, but you can always click this button and look at your logs file. Now, where is this logs file? Well, the answer is it's where you set it to be. So if I go to application settings, you can see that it defaults to here. And this logs pane is really useful for basically print logging. This is basically where you will find the ability to debug by printing to terminal, which is a pretty, if you've ever programmed in your life, you know how important that is. And it's really easy to use the logger. Now, I just noticed in the generation of this starter file, I didn't actually include the necessary things you have to write to invoke the logger. So I'll definitely add that in before I publish this video. But if in case it's missing, what you want to do is say import logging. And then you want to say logger equals logging.get logger underscore underscore name underscore underscore. You don't have to think about, don't bother thinking about what these mean if you don't know what they mean. It doesn't matter. What this means now is that anywhere you want, you can insert logging messages. So for example, maybe outside of the for loop here, I'll say logger.info starting the simulation. And if I save that and then I return to Overseer and I run it again and we go to logs, you will see there it is. You see a message starting the simulation, and that's that. And so now what that means is that you can print messages to yourself. If you're debugging, this can be extremely useful. Now, I mentioned that there is a logger.info here. There's also logger.warning, logger.debug, logger.error, and logger.critical, I think? I don't know. Maybe not. The main ones that you want to use are logger.info, logger.warning, and logger.error. There's also logger.log, in which you give a log level instead of a type. For example, I think 22 would be info. Let me double check. Let me see if that even works. Yeah, it looks like that works. You see level 22, and I'm surprised that didn't default to info, but it did interpret as the log level, and I believe if I filter to warning, I won't see either one. Yeah, so basically, if I remember correctly, numbers 20 through 30 refer to info, are like info level logs. 30 through 40 are warning. 40 through 50 are error. You can look that up yourself. It's standard to Python itself. But yeah, so that's how you can use the logger there. And in the Overseer log, you can actually filter by level. So if you don't want your info logs, you can filter them out by just saying I only want warning and above, and then you'll see those logs. And I should emphasize that what you see in this logs pane is just being read from a text file, and you have that text file too if you'd rather. So if you go to if we look here. There it is. There's the logs file. Again, it is wherever you set it to being. But here's log.jsonl, and we can see it here, and it's just listed there as a JSON message for you to do whatever you want with. Error messages, like actual errors from Overseer or Python, will also both appear here. There's no distinction between actual internal Overseer errors and your simulation errors, which is for better and worse. If something breaks, you will see what happened there, and so that you can use that to debug your programs. So the last thing that is here by default that you're probably wondering about is this event queue here. And this event queue is kind of an advanced feature. Not a lot of people are probably going to use it, especially early on in their use of Overseer. But it's honestly a really cool feature that I'm really excited about. Basically what it allows is this event queue is something that Overseer itself has access to. And so you can use the event queue to create buttons, basically. Create button simulation controls that can be clicked on, which send commands to the running simulation. So if you have an iterative simulation, you can that simulation can choose to receive events and then process them within the simulation, meaning that you can send things to your simulation to be reacted to while the simulation is running. So to show you a quick example of that, let me come back to my Ian Wright model. So you can see that I've got these apply shock buttons. So this is an economy with commodities in it, and let's look at the rates of profit specifically here. What I can do is I can apply a technological shock. Basically, I can a CULS shock, that stands for capital using labor saving. So if I want to apply a capital using labor saving innovation to the economy, what this says is I would do it every it's none right now. But if I said fits and starts, then you can see that basically every 20 cycles or so it applies a shock to the economy. Now that doesn't use the event queue. That's just kind of happening every 20 cycles according to this parameter dt here. However, let me make it a little bigger so that you can so that the shocks shocks look bigger. So the shocks look pretty big now when they happen. And so watch this. I'm going to change this back to none. I don't know why it keeps resetting the camera. But if I'm going to make this run longer too, like 500. So if I click this, you can see it actually reacts. So this is how you can actually talk to your simulation while it's running. And the way that this works uses the event queue. So let me go ahead and jump into the code there so that you can see how that would work for yourself. And of course, this code comes with, this example comes built in with Overseer, so you can take a look at this yourself if you want to get a sense of how it's supposed to work. So let's go to capitalisteconomy.py, and let's go to the step function. So if you look at this, you can see it says, it takes a look at the event queue, it sees if it's empty. If it's not empty, then it processes what's in there, right? It just grabs what's in the queue, and the way that it works is that you can find more information about this on the wiki for Overseer, but basically it's just processing the command and then doing the thing. And so basically it's up to the user making the model to process what's in the event queue, but it's through the event queue that you can allow for a full back and forth interaction live between Overseer and your running simulation. So that's really cool. Another thing that should be said about this event queue is that you might have noticed this parameter change response. It sets as to widgets decide. By default, the widgets will default to being restart. What that means is that if I have a running simulation and I change this number to like 0.4, then it just restarts the whole simulation. However, if I change this to widgets decide, or if I change the send message, then what happens instead of the simulation being restarted, it'll simply send a message, it'll simply add to the event queue the event that your parameter has changed. And so you could update the parameters live if you want to. It's up to you to decide to process that. But for this particular model, it does work. I can change this to, if I want to change, like, let's say, this number here to like 0.5, then you can see that some stuff happens, right? That parameter changed and that has an effect on the system. So you can choose to have the parameters influence simulations as they're going for that in that way. So yeah, that's the event queue. It's an advanced feature, but it is a feature that it's there, and you might have wondered what it is. So that's that. Another more advanced feature that you probably don't have, but which can be witnessed here pretty well, is the idea of a metaparameter. So for example, this economy uses 3 commodities. It has 3 commodity types: corn, iron, and sugar. However, this is not a 3 commodity model. It's actually a more general model. You can increase the number of commodities. Like in principle, the number of commodities is arbitrary. And so there's a parameter here called n, which is currently set to 3, which is that number. And watch what happens when I change this number to 6. I now have 6 commodities. And you can see also, let me just click random so you get real numbers here. And you can see also that the dimension of the matrix A changed from a 3 by 3 to a 6 by 6 because the dimension of this matrix is a metaparameter, right? It's a parameter that parameterizes the parameter. And the L changed as well, and so did all these vectors that have to do, you know, so every parameter that is a vector that, you know, adjusts to the number of commodity types. They're all here. They've all changed at once. So you can have parameters that come around and influence the control panel itself. So it really, the sky's the limit in terms of, like, you know, the options you have here. It's a very robust system, and you can make really robust models using Overseer at this point. There's a lot of other features, but I think I've given you a good enough reason to go use it yourself if you want to. So 2 more little things I wanted to mention before wrapping up the video. One of those is the portability of the models you create. So you might notice that if you click this, you know, one of these models, you'll notice that that there's a file called demos.yaml or YML. This right here contains the information about every demo that uses this model. And that's contained within the model folder. And what that means is that you can just hand this folder to somebody else that's using Overseer, have them drop this model in their models folder, and then they have your model. It's that simple. They don't need to add anything else. It's fully portable. The models you create can be handed around, shared really easily. So that's fun. And then additionally, I mentioned in the mission statement of Overseer that part of the idea is that you can create kind of professional-looking, like, apps out of Overseer that you can pair with a paper you're writing or use for a specific kind of educational purpose as a communication tool. I'm not going to show you how to create that out of your Overseer model here. However, you can find that on the wiki page if you go to feature model releases. If you go to feature model releases, you'll find the information that you want in order to create. But basically, you know, there are some secret features that you can use to kind of hide more developer, I guess, driven features, so that it only contains the information that somebody, like, exploring a model would need. And then additionally, if you go to the GitHub page and go to release, there's a whole bunch of scripts and things like that that you can use in order to create packaged apps that don't actually require the user to have Python installed at all. So you can create out of Overseer some fully portable apps that you can just kind of pair Mac and Windows versions of for a user that will basically hand them something they can open without having any other special things installed on their computer, and they don't really even have to know what Overseer is, but they'll still be able to use the model that you've created. So that's kind of how that works, but I'm not going to get into the details of how to do that here. You can find the information that you need on the wiki. So I think that's where I'm going to leave this tutorial video. It's gone on long enough. I might make a future video if people really want it, doing something a little more advanced, like maybe making an agent-based model. But keep in mind that Overseer itself includes many of the models I built myself as examples for you to go off of. And then also you can also find some more advanced examples in the Read the Docs wiki page, which also includes a lot more comprehensive documentation on Overseer and all of its advanced features. It's got a lot of things that I didn't get to. If you encounter any bugs or have feature requests, feel free to create an issue on my GitHub page for Overseer. Another thing I should mention is that if you have a model which you've made using a different programming language and you just want to make an interface for it in Overseer, you can. You will have to do some programming in Python. You'll have to set up a layer that basically receives log messages from your simulation and then processes those logs into the aggregated data. An example of that, however, can be found. You don't have to reinvent the wheel, though. We've done that already for my labor time economy project, which is a simulation that's been written in C++. And so if you click this link here, you'll get sent to the GitHub page for that, and you can look at the Overseer model I've built for it and see how we've done that. You should be able to honestly copy and paste a lot of it in order to just make it work. And also the Read the Docs page has some more information on that as well. In any case, I hope you find the tool useful. I'm very excited about it. I'm excited to utilize it potentially in my future videos and in my research. It's the kind of tool that I've always wanted to have, and now I have it, and I hope you find it useful too. So thank you for watching.